Okay, so today we're going to prove Euler's identity. This is one of the most important results in maths, and it has the ability to excite people's passions in a way that few other equations can. Feynman has described it as the most remarkable formula in mathematics. The depth of feeling that it inspires in people can be seen by the fact that people are willing to get it tattooed on their bodies. This appears to be a young woman who has got it tattooed on her back. If you Google Euler's identity tattoo, you'll see that she's not the only person who's done this. I think it's safe to say that there aren't any mathematicians in the world who don't really cherish this equation. It's one of the deepest, most profound results in maths, and it's actually quite hard to convey quite how important it is to the uninitiated. You know, if a non-mathematician's seen that tattoo, they'd probably be horrified or perplexed, to say the least. And we've also got Euler here, the guy who first figured this out, and widely regarded as, if not the most important mathematician of all time, certainly in the top two. It's basically a toss-up between him and Gauss. No one else comes close to those two, really. But most people would probably go with Euler as being the number. I mean, he's certainly the most prolific mathematician who ever lived. Okay, so let's look at the details of the proof, or some information about the proof before we start. So it's not a very difficult result to derive. All you really need to know is some elementary trigonometric functions, sine, cosine, and we're also going to use Taylor series and Maclaurin series. So if you haven't seen those before, we'll briefly review them, but they're essentially infinite series expansions of those trigonometric functions, or it doesn't have to be trigonometric functions. You could Taylor expand any analytic function, but we're going to use the Taylor expansions for the trigonometric functions that you see in high school trigonometry. So this result it belongs to the areas of complex analysis and analytic geometry, even though those subjects tend to be more advanced than this result that we're looking at today. Complex analysis, of course, deals with functions of a complex variable and notions of analytic functions in the complex plane and so on. This is a more elementary result than most of the things that you would encounter in a complex analysis course, and analytic geometry is almost a fancy way of saying the kind of plane geometry that you learn in high school. You know, shapes in the plane, angles, triangles, all that stuff. So Euler derived this result in around 1740. It wasn't published until 1748, but needless to say, it's been around for quite a while now, and it continues to inspire people's imaginations and make people determined to learn more maths. So let's just look at what the equation actually says. E to the I pi plus 1 equals 0. Now, if you don't recognise all of these numbers, we can just briefly explain what they are. Of course, everyone ought to know what 0 and 1 are. You could argue that these five numbers, or these five quantities are the most important constants in mathematics. Certainly, it's hard to overstate the importance of the numbers 0 and 1. They come up in all kinds of contexts for all kinds of reasons, and they are enormously useful concepts. E, of course, is the base of natural logarithms. So this is a number that you would see in all kinds of different contexts, such as population growth, compound interest, radioactive half-lives, and this is the number that we use to model all of these exponential rises and exponential growth, exponential decay, and so on. Pi, of course, is the ratio of a circle's circumference to its diameter. It's a transcendental number, which means it's not the solution to any polynomial equation that you can write down, and it's the same constant that appears in any circle will have pi as its ratio of circumference to diameter, no matter what circle it is. And finally, I is the imaginary unit. So if you've never heard of imaginary numbers or complex numbers before, these were first invented / discovered for the purpose of solving equations such as x squared equals -1, or equivalently x squared plus 1 equals 0. Now, you should know from high school algebra that there isn't any number any real number you can write down or you can conceive of where when you multiply it by itself you'll get a negative number. Whether you start with a negative number or a positive number, multiplying it by itself will always give you a positive number. So it seemed to be the case that this equation would just have no solutions. And of course that is the case if we restrict ourselves to real numbers, but we can invent a new number I, and we can give it the definition that I times itself equals -1, i.e. I is the square root of -1. And this allows us to take roots of negative numbers, so we could have square roots of other negative numbers that we can express in terms of I, and this number I allows us to extend the real numbers into what's called the complex numbers, where we form pairs. We'll look at the complex plane now. So no doubt you'll remember the XY plane from analytic geometry in high school, when we dealt with points in the plane or shapes in the plane or whatever. Now what we're going to do is, instead of x and y, we're going to have a real axis and an imaginary axis. So we can think of a number z, which is x plus I y. So the real part of z is its x component. You know, where on this left-right axis is it? The imaginary part of z. Denoted in z is equal to IY. So this is the imaginary axis. So a number such as 2 plus 3i would be 2 roughly here. This would be 3i. This would be 2. So this point in the plane is a complex number, and this entire plane of complex numbers is called the complex plane. So complex analysis deals with these kinds of constructions where we look at functions of a complex number z and try to recreate the familiar rules for differentiation of functions, or try to do calculus, differentiation, integration, etc. So that's the complex plane. Let's just go back for a second to the Euler identity. So at this point you might be thinking, okay, I think I know what these numbers are, but why are they connected? And it doesn't seem obvious that these numbers should be related to each other. Exponential growth, circles, imaginary numbers, 1, 0. On the face of it, there's no reason to assume that these things should have anything to do with each other. And that's a big part of why people find this equation so profound, because it pulls all of these ideas together in an extremely concise, elegant equation. So let's look now at some trigonometric functions. So we could draw the unit circle. See how well I do this. That's not too bad. Right, so this isn't the complex plane, this is just the... Well, actually, yeah, let's do the complex plane. So if we draw a circle, so all the points on this circle are 1 unit from the origin. If we draw a circle here and we draw a triangle inscribed, this should be a straight line. So here we have a right angled triangle. This inner angle is theta. So there's the triangle inscribed in the unit circle. You can just blow it up a bit so that we can see better what's going on. So it's something like this. It has a right angle here. This angle, theta, will be of interest. So we know that the unit circle, so this point is on the unit circle, so it's 1 unit away from this point. So this hypotenuse must be one unit long, and then the cosine of the angle theta will be equal to adjacent over the hypotenuse, and the hypotenuse is 1, so it's just equal to this length here, and the sine will be equal to this. So the sine of this angle will be equal to the opposite over the hypotenuse, which is just the opposite because the hypotenuse is 1. So the x, the bottom of the triangle length will be the cosine of the angle, and this will be the sine of the angle. But of course, we're in the complex plane, so the lengths along the imaginary axis are imaginary. So the point x plus iy, which remember we're going to call the number z. This number here, we can also express it as cosine theta plus I sine theta. Okay. So I want many than this. Right, so that about covers well, the unit circle and where the cosine and sine functions figure into this arrangement with the triangle inside the circle. Of course, we're only looking in the first quadrant here, where x and y, or x and I y are both positive. Well, x and y are both positive. This would hold in all of the quadrants. It's just easiest to illustrate in the first one. So we're going to look at Taylor's theorem now. This is a result we're going to need along the way to prove Euler's identity. It's a theorem regarding continuous differentiable functions that we can re-express using an infinite series expansion, or if not an infinite series expansion, a series expansion that terminates at some point, and then the difference between it, so the approximation will get better the more terms we include. If we can include infinitely many terms, then the approximation will be exact. If we only have a finite number of terms, then there will be some error that depends on how close we got to the true function. So you see here that f of x, well, first of all, f is a real valued function of a real variable, so it maps from r to r, and we're going to say that it has k plus 1 continuous derivatives, i.e. we can differentiate it k plus 1 times in some neighbourhood of x equals a. So we're going to Taylor expand the function f around a point a, and we're going to Taylor expand it in some neighbourhood of that point, and we're calling that neighbourhood u. So for any real number in this neighbourhood, then the function f of x can be expressed as the value of the function at the point a plus the first derivative of the function at the point a, evaluated at a, multiplied by the difference between x and a, plus the second derivative evaluated at the point a divided by 2 factorial times the square of the distance between x and a. And the pattern continues. You take the third derivative divided by 3 factorial, the fourth derivative divided by 4 factorial, and you take the kth power of x minus a. So we're only really restricted here by the number of times we can differentiate the function. If there's some limit, if we can only differentiate the function 5 times, then we'll only be able to get up to 4 terms in the approximation before we can't differentiate it anymore. So the final term here, expressed as an integral, captures how far off we are from the true function, and we won't really bother proving this theorem at the moment. But you can see here at the bottom we have the red curve is the exponential function, and we start off with a linear approximation, and then a quadratic approximation, a cubic approximation, a quintic approximation. So you see here that as you add a second term, a third term, a fifth term, the approximation gets closer and closer to the true exponential function. And indeed, if we let the series progress through infinitely many terms, then we will exactly recreate the exponential function. And the exponential function happens to be one of these functions that we can differentiate as many times as we like. So it's an ideal function for this kind of thing. So let's expand the Taylor. Let's look for the Taylor series, or the Taylor expansion of e to the x next. Okay, so I'll leave up Taylor's theorem there. We're just going to get rid of that graph, and we can express e to the x now as so e to the x. That will be our f of x, the function we're interested in. A in this instance will be 0. So a Taylor series is the name given to these expansions when they are performed in general. If you expand around the point 0, then the name for that is a Maclaurin series. It's also called a Taylor series because a Maclaurin series is a special kind of Taylor series where it's a more limited case. But you may also hear that name. So the function e to the x, we can express it as e to the 0, so that would be the function evaluated at 0, plus the derivative. So what properties of derivatives? Let's just remind everyone that the derivative with respect to x of e to the x is e to the x. So it's one of the remarkable special properties of the number e, and the property that makes it the base of natural logarithms is when you differentiate e to some variable with respect to that variable, the rate of change is equal to the function itself, i.e. the gradient is equal to the value of the function, and that's true at all points on the curve, and that's the thing that characterises exponential growth. In fact, so e to the x equals e to the 0, that's the first term, and then we want to differentiate, so that's going to be e to the x again, and that's going to be e to the 0, so we're evaluating it at a, which is 0, and x minus a is just x. Right, and then we'll get the second derivative evaluated at 0. So e to the 0, we should add any number to the power 0 is always 1. Let's not go into that, but this is something you should memorise. You know, no matter what number you raise to the power 0, your answer is always 1. So we're going to get 1 over 2 factorial x squared plus 1 over 3 factorial x cubed, and of course these first terms, this is just 1 plus x plus, so we can tidy up, just start to see the pattern, x squared over 2 x cubed over 3 factorial x to the 4 factorial, etc, etc. And we can add as many of these terms as we like, and the more terms we add, the closer we'll get to the real exponential function. And if we let the series sum from 0 to infinity terms, where that index refers to the derivative you take in the term, then we will recover the real the true exponential function. So we've discovered that the Taylor series for e to the x is this 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial plus x to the n over n factorial. Now we want to do the same for the trigonometric functions. Okay, so rather than going through the same process for the cosine and sine functions, I've just summarised the results here in this box. So the e to the x expansion, we derived that a moment ago. The cosine expansion, let's just look at this and how it compares to the function briefly. So f of x is the cosine of x, the function we want to expand. We evaluate cosine at 0, cosine of 0 is 1. Then we want the derivative of the cosine evaluated at 0. The derivative of the cosine is minus the sine of x. Evaluated at 0, sine is 0. So this term drops out, and we don't get any term that's linear in x. The next term gives us the a, remember, is 0, so we just get an x squared term here, and the coefficient in front of it this time is minus 1, because we're evaluating the second derivative of cosine, which is minus cosine, and minus cosine of 0 is minus 1. And then the pattern repeats, so the cubic term vanishes because it has a sine of 0 in it. Then the fourth term again is plus 1. So we end up with an alternating series where the sign alternates, but we're only left with the even powers, i.e. the even polynomials in x. and that makes sense because cosine itself is an even function, and remember an even function is one where the function f of x is the same as f of minus x, i.e. if you flip the input into the negative, the output will be the same, so it's symmetric about the y-axis. And an odd function is one where if you flip the input, you flip the output sign as well. So the sine function is odd, and we see here it's only got the odd terms in it. And you can work this out for yourself if you want to check it. So let's get rid of the statement of Taylor's theorem and evaluate a slightly different version of the exponential function. What happens if we evaluate e to the I x? Now, this is a complex number that we're evaluating, but the Taylor series for complex numbers is the same as for real numbers. We just use a complex number instead of the real number x. So if we plug in our formula, if we plug ix into this formula, we get 1 plus ix over 1 factorial plus ix all squared over 2 factorial plus ix cubed all cubed over 3 factorial. Let's just do ix to the 4 over 4 factorial. Now, I is the imaginary unit, as we explained earlier. When we square I, we get minus 1 by definition. I is the square root of minus 1. I cubed is I squared times I, which is minus 1 times I, which is minus I. And I to the 4 is I squared times I squared, which is minus 1 times minus 1, which is 1. So you can imagine that if you're on the complex plane, you start at 1, multiply by I, you come out to I, you multiply by I again, you come out to minus 1, multiply by I again, you come out to minus I, and every time you multiply by I, you just cycle round these points. Okay, so now let's look at, let's get rid of that, let's look at tidying this up a bit. Right, 1 plus, now we'll group all the real terms together, so this one, I squared gives you minus 1, so that'll be minus minus x squared over 2 factorial, and then we'll get a plus x to the 4 over 4 factorial, and then we'll get a minus, and it'll be x to the 6 over 6 factorial, plus, and so on and so on. And we can group all these terms together, separate them out, and then we have all the other terms that we didn't include in this bracket. They'll all have a factor of I common to them. We factor out the I, then we can write the rest as x, that's this term, minus x cubed, oops, minus x cubed over 3 factorial plus x to the 5 minus, and so on. And you can see where this is going, I hope. So this bracket is the Taylor series, or the Maclaurin series for cosine. So we've really got cosine of x plus I sine of x. In other words, e to the ix is equal to cosine of x plus I sine of x. And this is called Euler's formula. Let's just go rid of this bit up at the top here. And we'll evaluate the function, or evaluate this relationship that we've just determined for e to the ix, but we'll look at it for a specific value of x, namely pi. So we'll see that e to the I pi is equal to cosine of pi plus I sine of pi. Cosine of pi radians is 180 degrees. The cosine of that is -1. And then sine of 180 degrees, or sine of pi radians, that's 0. So we have I times 0, we have -1 plus 0, which is -1. Now, we could leave it at that, or we could add 1 to both sides and get that e to the I pi plus 1 equals 0. And that is Euler's identity. I think I'll cut this video here because it's getting quite lengthy. There are some other important theorems that you can derive as corollaries of this, and we'll look at them in the next videos.